Okay, I thought we'd get started with some problems on 2.6. They're kind of weird at first, and then you get the hang of them, and they're all right. It says assume that x and y are both differentiable functions of t, and find the required values of dy dt and dx dt. So we're going to differentiate these, but we're going to do it with respect to t. And again, that variable's not in the equation, but these both y and x could be written as a function of t, and we just don't know what it is. So if we go to take the derivative of here, the derivative of y would just be dy dt because we're taking the derivative with respect to t. And then let's take the derivative of the right-hand side. I'm going to go ahead and rewrite that as x to the 1/2. It would be 1/2 x to the negative 1/2. And then we don't know what we got to kind of use the chain rule idea. It's times dx dt because we don't know what the derivative of x is with respect to t. So we have to do this. And so dy dt, if we want to simplify this a little bit, would be 1/2 square root of x dx dt. Okay. Now, if I want to find dy dt, I've already got it solved for dy dt. So for a, if I'm given that x is 4 and dx dt is 3, I'm just going to plug that in. Dy dt would be equal to 1/2 the square root of 4, plugging that value up here in, and then dx dt is 3. So instead of writing dx dt, why don't I just plug in the 3? So that would be 3/2 times 2, which would be 3/4. All right, now part B says find dx dt when x is 25. And they tell you dy dt is 2. So maybe we know the rate of change of the other variable is what's going on in these problems. We're trying to find dx dt, but we know dy dt is 2. Maybe that's some kind of rate of change going on with the y's, and we're trying to find what the rate of change with the x's are with respect to t. Now what I got to do this is take that equation that and solve it for dx dt. And if you remember what you're going to do, you're just going to multiply by the reciprocal of this mess over here, which would be just 2 square roots of x over 1, and I would do that to both sides. So I end up with 2 square roots of x dy dt is equal to dx dt. And so now if I want to do the b part to find dx dt, all I got to do is plug in x is 25, and I just write it over here in blue. We can see where we plug it in. And this dy dt is actually 2. So it would be the square root of 25 is 5, 2 times 5 is 10, and 10 times 2 is 20. So 20 would be dx dt. We're just evaluating this expression after we find the derivative of it. So there's our B answer right there. So if you notice what we did, to kind of recap, we used implicit differentiation with respect to the variable t, which means both of these variables will have this dy dt, dx dt thing show up because we don't know what they are with respect to t, so we can't state it. And then we're just going to solve for the one that we need. If we've got dy dt solved for, all I got to do is plug in this given information up here. If I want to find dx dt, I'll need to solve for dx dt first, and then I can plug the information in. I thought I would get to 5 just to pick a couple of different things to do on one video. Y is x squared plus 1, and they say a point's moving along the graph of this given function so that dx dt, usually this dt is just time, okay? Dx dt is 2 centimeters per second. Find dy dt for the given values of x. And so our given values of x, a is -1, b is 0, and c, x is 1. Okay. So first of all, what I got to do is take the derivative of this with respect to t. All right. So if I'm taking the derivative of y with respect to t, it would be 1, but then dy dt. Now the derivative of x with respect to t would be 2x, but dx dt. Oops, that does not look like an x. Dx dt. And then the derivative of the 1 constant on the end is 0. So they want me to find dy dt, and we know that dx dt is 2. So it's already solved for dy dt here. So what I'm going to do is just plug in the different values. For a, x is 1, and remember this dx dt, they told us over here it was 2. centimeters per second. So this is going to be 4 centimeters per second for part A. Okay. For part B, we're going to do the same thing again. dy dt is 2 times x, but this times x is 0, and dx dt is 2 centimeters per second. All that's still going to be 0, isn't it? Because we had the 0 in there. So 0 centimeters per second. And then for the C part, dy dt is 2 times x, but x is 1 this time. Or wait, there's supposed to be a negative 1 in there. Oh, A, it was negative 1, wasn't it? So this would be negative 4 centimeters per second. Now it's positive 1. I just probably didn't catch it. I wrote it down there. Okay, C part we are plugging in 1, and then dx dt is still 2 centimeters per second. So this would be 4 centimeters per second. So probably what's happening, if you look at the difference between A and C, since A is negative, it's probably slowing down. C is positive, it's probably increasing at that point. Okay, I thought I would do 13 next, just because I know there's just so much here that can get confusing each problem. Find the rate of change of the distance between the origin and a moving point on the graph of y equal x squared plus 1. If dx dt equal 2 centimeters per second. All right, they said they wanted the rate of change, which is our derivative. Remember, slope, rate of change, derivative, all the same kinds of things. They said they wanted it for the distance between the origin. So it sounds to me like what they want is dd, which is distance, and we're going to have to go get the distance formula, over dt to time, okay? Because we're given this dx dt, we're pretty sure that's what we want. Well, if you remember, they said between the origin, well, the origin is the point 0, 0. So I've got a point here. My point here could be represented by x, and then the y value is x squared plus 1. So these are my 2 points right here. And I'm going to plug them into the distance formula. Now, the distance formula, if you remember, is the square root of your x minus x2 minus x1 squared. So I'll call this my x2, y2 here. And I'm going to call this my x1, y1 here. So x minus 0 squared, because remember it's x2 minus x1 squared, plus the difference in the y squared. So it would x squared plus 1 minus y2. y1 would be 0 squared. Well, that looks pretty... I mean, it really isn't as hard. Look, you know, if you think about it, I could have left those zeros off because they don't matter, do they? It would be x squared plus 1 squared. Now remember, let's multiply out x squared plus 1 squared, because that's really x squared times 1 times x squared plus 1. I think I said that wrong, but I wrote it correctly. That would be x to the 4th plus x squared plus another x squared plus 1. Okay, so if we put that all underneath here, that's the square root of x squared plus x to the 4th plus x squared. Well, over here that's 2x squared, so I'm going to add those 2x squareds together, plus 1. And it ends up being, and again, I'm going to put big D for distance. I guess I'm going to do that just because I know in a minute what I'm going to do with this. This should be a big D for distance. That looks bad. I'll fix it on the next line. This is the square root of x to the 4th plus 3x squared plus 1. Now, if I want the derivative of distance with respect to time, remember I might want to rewrite this just to help myself think to take the derivative a little easier. What if I wrote it this way? Okay, then the derivative would be a half of all that mess. And then you subtract 1 from the exponent, so it would be to the negative 1/2 power. And then what's the derivative of all that with respect to t? You'd have to take the derivative of the inside part. It would be 4x cubed plus 6x. And the derivative of 1 is just nothing. But then again, we don't know what that derivative is with respect to time. So each one of those variables would have a dx dt. I'm just going to put it after it instead of putting 4x cubed dx dt plus 6x dx dt. I'm just going to do it like that. One of the reasons I'm doing that is I know what dx dt here is, and if I keep it on the outside there, I can replace this right here with 2. 2 centimeters per second. Okay, so the derivative of d, distance, with respect to time, would be, now, okay, this 1/2 times this 2 way over here, they're going to cancel out, and I'm going to end up with this on the bottom. If you look at it, it's got this negative 1/2, so I'm going to have a fraction on the bottom. It's going to be the square root of, oh goodness, let's see if that'll fit in there. Of course it's not, x to the 4th, but hopefully you can listen, plus 3x, you know that's not going to look like an x no matter what I do, 3x squared plus 1 on the bottom. And on the top you've just got that 4x cubed plus 6x. And then it's centimeters per second, whatever's going on here. So that would be my derivative there, and that's all you have to do.